So in our previous video series, we looked at the idea of how to take derivatives as well as integrals with respect to vector value functions. And now what we're going to do is we're going to take a look at applications of those. So we're going to take a look at velocity, acceleration, and speed for vector value functions, and we're going to interpret that, and then we're going to take a look at some of the applications. So we know that velocity is just the first derivative of any function given the position. So if r of t defines the position to where r of t is f at ti plus g at tj plus h at dk, then if we take the first derivative of that function, that gives us the velocity. The second derivative gives us the acceleration function at any time t or any parameter t. To find the speed, we just find the magnitude of the derivative. Alright, so just a couple examples, and these aren't meant to be difficult. We want to try to find, given the position function for some object I in space, find the velocity, speed, and acceleration of functions for that object. So we have this 3t plus 3ti plus tj plus 1/4 t squared k. Alright, so v of t, which is going to be the first derivative. So let's find v and sine, or the speed. So v of t, which is equal to r prime of t, is going to be equal to 3i plus j plus 1/2 tk. Right? And that's all there is to it. Not meant to be anything too difficult. The magnitude of the velocity, which is our speed function, is going to be equal to the square root of 3 square plus 1 square plus 1/2 t square, or in other words, that's going to be the square root of 10 plus 1/4 t square. Right? So this is our velocity function, this is our speed function, and then finally the acceleration function, which is our second derivative. That's going to be pretty easy. We get 0i plus 0j plus 1/2 k, or in other words, 1/2 k. All right, so if you can find a derivative, you can very easily find both or all three of the velocity, acceleration, and speed functions. All right, one second example. All right. So we have this function w of t, 2 cos t, 2 sine t plus t squared k, and the I and j respectively. You might remember that when we first started vector value functions and we graphed this was a helix, and it spirals around the z-axis. Okay, so it might be helpful for you all to kind of keep in mind some of these more common types of vector value functions. Now this one that we had before, that's just a polynomial. It's going to kind of jet out from the origin out into space, all right, as t gets bigger. But this one's more cyclic, and it does kind of wrap around that z-axis. So anyway, and I do encourage you all to use that grapher from GeoGebra to verify what these look like. So w prime of t, which is our velocity function, is going to be equal to -2 sine t I plus 2 cos t j plus 2 t k. If I was to find the speed by finding the magnitude, that's going to be equal to the square root of -2 sine t squared plus 2 cos t squared plus 2t quantity square. All right. Now we can simplify this, and we should. That's going to be equal to the square root of 4 sine square t plus 4 cos square t plus 4t squared. We know that sine square plus cos square is 1, so if we were to factor out a 4 and use that Pythagorean identity, we can write this as 4 plus 4t squared. And one final way to write this is by factoring out a 4 and then taking the square root of 4. We can write this as 1 plus t squared, or 2 times the square root of 1 plus t squared. That's probably the most simplistic algebraic answer we can get instead of having that trigonometric answer. All right, so just be aware that we do try to simplify as much as possible to get rid of trig stuff when possible. Right? Now finally, we're going to find the acceleration function, a of t, and a of t is going to be equal to negative 2 cos ti, and all I'm doing is I'm just going up here, taking the derivative of each of these terms from the velocity function, minus 2 sine t j, and then finally plus 2k. All right, so that's easily how we're going to find acceleration, velocity, and speed functions. All right, so applications. So what if we wanted to go backwards? All right, what if I gave you the acceleration function or the velocity function, and I wanted to go back and find the velocity and the position vectors? So there I gave you the position vector, now we're going backwards, okay? And then we're going to find the position at time t equals 2. Well, the good news is this problem is exactly like the one that we did in the previous section where we integrated term by term and then used the initial conditions. All right, so now notice that the initial conditions for this one are 0. So this one's going to be ridiculously easy. All right, so let's just go term by term. So we're going to integrate dt, okay, which is 1. So that's going to be t plus c1. And we know that, so this is actually going to be our velocity function. Right? So when we substitute 0 back in, 0 plus c1 is equal to 0, which implies c1 is equal to 0. Right? We're going to integrate the exact same thing for j and k, and obviously we're going to get the same response. So 0 plus c2 equals 0, which implies that c2 is equal to 0, and then not surprisingly, equals 0, and that means that C3 is equal to 0. All right, so the good news is all these C's go away, and we're just left with T, T, T for the velocity function. So our velocity function, V of t, is going to be equal to Ti plus Tj plus Tk. All right, now we need the position function. And we did say that the position function at 0 is equal to 0. So we're going to see something very similar to the previous, where all of our constants are going to go to 0. Right? So now we're going to integrate t with respect to t. That's 1/2 t squared plus c4. We're going to substitute 0 in. And that means that c4 is equal to 0. And the exact same thing is going to happen for the other two. So 1/2 t squared plus c5, 1/2 of 0 squared plus c5 equals 0, and that goes away. And then finally, integral of t dt, 1/2 t squared. And again, all I'm doing is I'm integrating each of these t's, which are the coefficients of I, j, and k. So even though I'm doing this repetitive process, it may be different in other problems. So we get 1/2 of 0 squared plus c6 equals 0. Right? So we can find that our position function, r of t, is going to be equal to 1/2 t squared I plus 1/2 t squared j plus 1/2 t squared k. And that's it. All right. So it's actually an old problem that we did, all right, which is good news because it's just an application of that initial value problem that we looked at in the previous section. One last example, and then we can move on to further applications. We have an acceleration function e to the ti minus 8k. The velocity function at 0 is 2i, 3j, 1k, and r of 0 is equal to the 0 vector. All right, so again, term by term, e to the t dt, that's going to be antiderivative of e is e to the t plus c1. Okay. And when we substitute 0 back in, e to the 0 plus c1 is equal to 2. Right? And hopefully it's clear that C1 is going to be equal to 1, because this would be 1 plus C1 is equal to 2, which means C1 equals 1. Right? So we're going to hold on to that. There's no J term, so that means we just get a C2, and C2 is going to be equal to 3. So that one was easy. And then finally we have this negative 8. So we're going to end up with negative 8t plus C3. And when we substitute 0 back in, we should get 1. So negative 8 times 0 plus C3 equals 1. And that means that C3 is going to be 1. All right, so our velocity function, v of t, is going to be equal to e to the t plus 1 I, because remember we got 1 for C1, plus 3j plus negative 8t plus 1k. Right? So that's our velocity function. Right? Now we have to find the position function. All right? And then we're just going to integrate again. And we know that this time r of 0 is equal to the 0 vector. All right? So everything's going to be equal to 0. Once we start computing, that doesn't mean the c's are going to be automatically equal to 0. All right, so we're going to integrate e to the t plus 1 dt. That's going to be e to the t plus c4. When we substitute 0 back in, e to the 0 plus c4 is equal to 0. And since e to the 0 is 1, that means that c4 has to be negative 1. We have the 3 for j. This one's going to be pretty easy. So 3 to the t, or 3t is the antiderivative of 3 plus c5. And when we substitute 0 back in, that should be equal to 0, which means that c5 is going to be equal to 0. And then finally, integral of negative 8t plus 1 dt. It's an 8. Right? So that's going to be equal to negative 4t squared. So we add 1 to the exponent, and then we divide by the new exponent, plus t, antiderivative of 1 is t, and then finally plus a c6. Right? And then the good news is for this one, all the zeros are going to wipe out everything, and c6 is going to be 0. So notice that's negative 4 times 0 plus 0 plus c6 is equal to 0, which implies c6 equals 0. Right? So now we can go ahead, we can get to our position function. All right? And for our position function, that's just going to be r of t is going to be equal to, right? So remember up here we had e to the t plus t minus 1 I plus, remember we had 3t for j, and then finally we just have this negative 4t squared plus t for k. And one last thing that I neglected to do for the previous problem is that we have to find the value at 2. All right, so remember it says find the position when t is equal to 2. So r of 2 is going to be equal to a half of 2 square I plus a half of 2 square j plus a half of 2 square k, or in other words, that's going to be 2i, 2j, 2k. So that's our vector at time 2, the position of it. So 2, 2, 2 in octant 1. And then down here, r at 2, this one's not going to be as nice. All right, so that's going to be e squared plus 2 minus 1 I plus 3 times 2j plus negative 4 times 2 squared plus 2k, or if we simplify that, that's going to be equal to e squared plus 1I plus 6j minus, because that's going to be negative 16 plus 2, so that's going to be negative 14k. All right, so hopefully this gives you a good overview of velocity, acceleration, and then going backwards from the position function to get the velocity and acceleration, as well as having the acceleration function and getting the first two, the velocity and position functions. So in the next example, we're going to take the next set, we're going to take a look at projectile motion, and we're going to derive a formula for that, and then we're going to implement that into a series of problems.